session of Math Divulged. Today is probably was probably a kind of unique day to be holding Math Divulged because it's Juneteenth and technically it's a holiday, but since we didn't and we didn't remember this beforehand, we already broadcasted that we would be having this lesson, so it's a balance between, okay, there's this holiday that's very important, and there's also Juneteenth, and there's also we said we didn't take this into account beforehand. So I guess the compromise we're going to have for today is to try to tie in computational biology to themes related to Juneteenth as much as possible. Okay, so something that has been affecting us, all is coronavirus. And so I guess we can start off with that, but first off, Juneteenth, it's important to acknowledge, it's important to acknowledge the emancipation, the freeing of the slaves, except for the one exception in the Emancipation Proclamation, that prison labor is unfortunately still used. So we still have to confront the legacies of slavery today, and so these legacies show up in our healthcare system as well, and that's how we're going to tie it in with computational biology. We're going to start off by looking at COVID-19. Okay, so for COVID-19, the first thing with COVID-19 is that there are that we want to know how it's impacting people, and we want to know how it's impacting people so that we can intervene properly to save as many lives as possible. And so to know how COVID-19 is spreading, we model it, right? So in a model, what you do is you see what's important and you track them. So what's important in COVID-19? And let me see if I can see the chat at the same time. It's possible that I can't. Yeah, I'm not sure if I can see the chat, so I'll just be doing this lecture style. And again, I don't know everything about, I'm not like an expert in this. I just study integrative biology and applied math at college. So so I'm just going off the best I've learned from my classes. So um, what we do in modeling COVID-19 is we want to know, for example, like how fast it's spreading so that we know, say, like when to lock down, stuff like that. And so to model the spread, we have to know who's infected, right? So there's an infected class, we call this I. But the rest of the people, what's their status, right? The infection, COVID-19, coronavirus, um, so coronavirus infects people who are susceptible, right? So it's not just something within this infected class, but it goes, but infected people actively infect susceptible people. So there's also an S class for susceptible. And then, and then so, and then besides who's susceptible and who's infected, well, once you get COVID-19, there is a mortality rate. So um, we'll say that, call that alpha for the mortality rate. But there's a good chance that you recover. So hopefully, if you or a family member get COVID-19, you recover. And so there's a recovered class. And what's different about this recovered class is that they have antibodies to COVID-19. Uh, so in a way, they're different from the susceptible class because it's not as easy for them to get reinfected. Now, the antibodies might wear off over time, but for in the simplest model, there's a susceptible class, an infected class, and a recovered class. So what happens is that people who are susceptible get infected at some rate, um, and that depends on a few factors. Um, and then people who are infected recover at a certain rate, like how many people per day. So to take into account, to model it, the most important thing is to know how it changes, the dynamics of it. And so change, one easy way of seeing change is, thinking of change is, how many people are in this class the next day versus today? How many people will get infected tomorrow versus today? So to say, so how many people will get infected tomorrow, will be infected tomorrow, is is the number of people in the infected class of tomorrow. So say today is T, so tomorrow would be T plus 1. And then how many people are infected today is I for infected sub T. So how many people will become infected is I T plus 1 minus IT. The number of people infected tomorrow minus the number of people infected today. And so similarly, we can we can track the changes for S and R, the number of people who are susceptible and the number of people who have recovered. So S sub T plus 1 minus S sub T. That's what we're tracking. And similarly, we track R sub T plus 1 minus R sub T, the change in number of people recovered. So if you haven't seen this notation, it's okay. It's just a way we write it. But basically we write change using this symbol called delta. And delta is basically like how we write change, and so S sub t plus 1 minus s sub t is the change in s, the change in number of people susceptible. I sub t plus 1 minus I sub t is delta I. Let me first make sure. Okay, and also make sure to send your problems to or your questions to Naveen, because I can't see the group chat. So yeah, I just saw that there were some people who messaged me in the group chat, and I can't do that at the same time. So I'll go back to the whiteboard, but yeah, please message Naveen if you have any questions. Okay, so there's a susceptible class, an infected class, and a recovered class. And then there's and then the change in the number of people susceptible is delta S, and change in the number of people infected from time t to time t plus 1, so today to tomorrow, is delta I. And then the change in the number of people who have recovered is delta R. So hopefully this is a good number. Okay, so first let's look at the change in the number of people susceptible. So for someone to, for the number of people susceptible to change, for say like there are this many people susceptible today and this many people susceptible tomorrow, what changes is the number of people who have from the susceptible class who have been infected, right? So that's yeah, this number, this right here is, well, actually no.
Brian, you appear to be muted. Brian, you're muted right now. Okay.
Thanks, Naveen. Sorry, I was muted. So I'm not sure how much was sort of lost, but I'll just do a quick recap. There's a susceptible class, an infected class, and a recovered class. And we want to know how these numbers change over time so that we can model it. And so there's a number of people who go from being susceptible to being infected. And that number is taken away from the number of people susceptible. And it depends on a few factors. It depends on the number of people susceptible. So if you have more people susceptible, then there's more people who might be who have a potential of being infected, right? So as the number of people susceptible increases, the transmission increases. And if there's more people infected, then there are more people to infect the susceptible people. So as I increases, this transmission also increases. And then there's so it's something times S times I, right? And that something is the transmission rate, beta. So beta Si goes from being susceptible to being infected. And that number, this number is taken away from the number of people susceptible, but is tacked on to the number of people infected. So that's plus beta Si right here. But that's not all. How else can the number of people infected change? And one way it can change is if someone infected unfortunately dies. So here we have the mortality rate alpha, and so unfortunately alpha times I people die. But there's also people who hopefully recover, and that is also dependent on I and by a factor called gamma. So the recovery rate. So beta is the transmission rate, alpha is the mortality rate, and gamma is the recovery rate. So hopefully people recover, and gamma times I people, if gamma times I people recover, then we have plus gamma I. And so with this plus gamma I, these people go from being infected to being recovered, and the number of people recovered also increases by gamma I. So now we have, we described the change in S, the change in I, and the change in R. Well, the thing is, it's kind of arbitrary to say T and T plus 1, right? Like at what point in the day are you keeping track of these? So it's, if we graph this, it would be like there's a point for day 1 for S, a point in day 1 uh, for I, and a point in day 1 for R, and then for the next day it would change somehow, and these would just be like points, right? So the thing is, if we look at all the SIR graphs, all the models that are online, and all the models being done in real time, or all the data being collected in real time, they're more continuous. They're like, I kind of forgot the specifics, but they're more continuous. So instead of keeping track at one point in time during the day, we model this continuously. And so to model this continuously, instead of tracking from one day to the next, what if we track from track how many people become infected in 12 instead of 24 hours, and have 12 hours. So st plus 0.5 minus s sub t. But then the rate would be different. It would, like, if it was linear, then to track it at 0.5 would half the rate. And so we have to divide by 0.5 to sort of even it out, right? If you've studied calculus, this might look really familiar. But basically, the thing is, instead of 12 hours, why not take this at, say, like 6 hours? So if 6 hours, then it would be 0.25, and then here it would be 0.25. And then the thing is, this number right here, 0.25, at first we had 1, t plus 1, and then this was 1, which did nothing. And then we shortened it to 0.5 and 0.25. And the thing is, we bring it closer and closer to 0. So what we have is this number epsilon. Now we bring closer and closer to 0. And as it approaches 0, we call this the limit, as e approaches 0, right? So this number gets, like, say it's this much. If e is 1, we have this much. If e is 1/2, we have this much. If e is if epsilon is 1/4, we have this much. And the thing is, it approaches some number, and as epsilon approaches 0, this number, we call it the derivative of s at time t. So ds dt. So what we're really modeling here is not S sub t plus 1 minus S sub t, the number of people susceptible in time t plus 1 minus the sum, like the number of susceptible people tomorrow minus the number of susceptible people today. But what we're actually modeling here is the derivative, the change, the instantaneous rate at which the number of people susceptible changes. And so that is that we write it ds over dt, and the number of people infected here, the change in the number of people infected, we write that di dt, and the change in the number of people recovered, we write that as dr dt. And you can look this up sometime. You'll get some kind of graph of, say, like this is the total population, and say at first everyone's susceptible, so there's no infected, no recovered, but then the number of people susceptible okay, so this is the number of people susceptible, yes, and there's no one infected and no one recovered, and there's an increase in the number of infections, and then as people become infected, people also start to recover, and so that there's that. And I kind of forgot how the actual model turns out, but you get some proportion of people susceptible, some proportion of people infected, and some proportion of people recovered, and that can help policymakers decide what policies around lockdown, around like wearing masks that they recommend. And of course, it's best to listen to like reputed sources like the CDC on wearing masks and stuff like that. But even if you wear a mask, if you get infected, no matter what you do, there's always a chance that you get infected. And that's especially bad with people with underlying conditions. And one thing about underlying conditions, trying to relate this to Juneteenth, is that in the aftermath of in the aftermath of like the Emancipation Proclamation. Yeah, Naveen put in the chat, I think infected should be minus gamma 1 instead of plus gamma 1. Yes, that is totally right. Let's see. Yeah, this right here should be, should be minus, not plus. But the thing is that in the aftermath of segregation, of the Emancipation Proclamation, there was still prison labor, because prison labor was still legally permitted for slavery. So there was still that, and then there was still segregation. And even in the aftermath of legal segregation, the systems that we have in place right now still disproportionately impact Black people in the United States. And so if we look here, yeah, so this is an article about how Black Americans face alarming rates of coronavirus infection in some states. So here are some links to specific data from specific states. For example, in Michigan, the cases by race are, well, there's more white people who have been infected than Black people. But then if you think about the number of white people in Michigan and the number of Black people in Michigan, and you divide it, right? So that you get the proportion, you see that it disproportionately impacts Black people over white people. There's like you can try to think of factors that might be affecting this, like segregation, that despite the legal outlaw of segregation, there's still segregation. And if we look here at Louisiana, so there's this particular geographical place here that's called Cancer Alley, I think. And so in that area, there are a lot of very polluting industries, and those industries center themselves around where mostly Black communities live, to exploit those Black communities. And so if we look at the data, Blacks are disproportionately impacted by coronavirus in Louisiana, and this is coronavirus deaths. So these are lives lost to coronavirus. Whereas if we look at the Black population of Louisiana, it's around 1/3. And we see here that a lot of these cases also have underlying conditions. And that brings us to another point, which is, by the way, this is just another more detailed SIR model. The thing is, with the SIR model that we went over just now, there's a lot of different cases. So you can have an exposed class. So it's not, you don't have to conform to SIR. You can add in an exposed class if that turns out to have a big impact. You can add in a healed class, alien, recognized. Yeah, I'm not sure exactly which one this is, but a lot of models for the COVID-19 pandemic have an SEIR model, so susceptible, exposed, infected, recovered. You just fine-tune the categories, the compartments, to how it best fits the current scenario. There's obviously other impacts, like having a lockdown and stuff like that might impact, for example, beta, the transmission rate. But yeah, there are a lot of different kinds of models, and compartmental models are just one of many different kinds of models. Okay, so yeah, as we see here, Blacks are very disproportionately impacted by coronavirus. There are many reasons. Some of them underlying conditions, and some of them also say being essential workers, like being Blacks being disproportionately being nurses, for example, and getting into these, especially in less well-equipped hospitals. And those could also be factors leading to the disproportionately high rate. What was it? Yeah, and also, and another factor is racial and ethnic minority groups are overrepresented in jails, prisons, and detention centers, which have specific, yeah. So you can read this statement. So how it ties with Juneteenth, I guess, is still, despite the abolition of slavery formally, there was still this exception for prison labor. And um, if you say watch uh, documentaries like The 13th, it goes over the historical criminalization of uh, systemic criminalization of black bodies um, in order to maintain a work a forced a the status quo of in order to maintain the supply of forced labor, which is extremely desensitizing. Um, yeah, and here here it goes through the same similar things, people in prisons and jails, and also people with disabilities. And so disabilities, some of them are underlying conditions, but some of them are, um, but regardless of, uh, regardless of whether a disability is an underlying condition or whatnot, there is a social model of disability um, which basically asserts that uh, which basically views disability from a social uh, disadvantage standpoint. And personally, having autism, there's this study that really that one of my friends shared. So um, the if we look at the cumulative probability of arrest by age 28, we see that people with disabilities have a higher cumulative probability of arrest than those without. So 42.65% of people with disabilities are arrested by 28 by age 28 have been arrested by age 28. People without disabilities have been arrested maybe 29.68% of the time. And if we look at the if we look at how this conflates with race, that's even more stark. So, uh, so actually, so this column is for people without disabilities, and this is for people with disabilities. Um, White people without disabilities are arrested this much. Black people without this much. Hispanic this much. People with disabilities, for white people, it's way more than without. For Black people, over half of Black people with disabilities have been arrested by age 28, and Hispanic people this much, which is very, very, in a way, to someone who hasn't uh, looked at this before, it would be very shocking. But this also points to ableist biases in police. So ableist and racial biases in police and policing that disproportionately uh, monitors communities of color. And what is it? Yeah, and these oftentimes, for example, social and verbal cues are interpreted differently by people with certain disabilities. For example, neurominorities, for example, autistics, um, and uh, and so yeah, those are a factor. But I guess in the interest of speaking about computational biology, there is uh, there is a particular uh, in the history of Black empowerment, there is uh, there is a okay. So sorry if this is like very disjoint, but hopefully, like, we kind of realized this being Juneteenth a little late, so this is a little, maybe a little disconnected, um, but there, but in the history of Black empowerment, who has heard of the Black Panther Party? Right, so when we think of the Black Panther Party, a lot of the images that are conjured are of a group of people protecting themselves and their community from police with guns. But that is only part of the big picture in history. The Black Panther Party also instituted a lot of social programs like free health clinics and sickle cell anemia screenings. So the thing with sickle cell anemia is that um, if we look at the genetics, uh, it mainly affects uh, people of African descent, some Indian descent, some and Indian subcontinent, South Asian descent, some here in Saudi Arabia as well. But a lot of this has to do with is correlated with the historical distribution of malaria, and this and with all correlations, we have to be careful. Correlation does not imply causation. We can there if you look up correlation does not imply causation, there you can find a lot of resources on that. But basically, um, malaria sort of uh, uh, balances out the sort of slightly balances the um, advantages and disadvantages of balances out the slightly balances out some of the disadvantages of sickle cell anemia. Um, because here we can see that um, so sickle cell anemia is affected by genetics, and so having in genetics, I'm not sure how many of you have learned this, but for each gene we have two alleles. Um, so we get one allele from the father's genome and one allele from the mother's genome, and so a normal blood cell would have um, these alleles, HB beta A and this, and then um, this is with sickle cell anemia, with one allele being the sickle cell allele, and this is with both alleles being the sickle cell allele. Thing is, sickle cell anemia appears when sickle cell anemia appears when you have both alleles being the sickle cell allele. If you have at least one of them being the normal allele, then you have normal red blood cells. And if you look at the mechanism for why, then it tells a slightly different picture. So although if you have one sickle cell allele and one normal allele, then your beta globin polypeptide production would look like this. This is not exactly the same as normal beta globin polypeptide production. So you might wonder, well, what effect does this have? If these if cells with this type of beta globin polypeptide production turn out normal in shape, and they don't have sickle cell, well, what other effects might this have? And it turns out that sickle cells are present. This having this trait means sickle cells are present, but you still have very you still have you still have normal red blood cells. Or okay, so you have sickle cells present at high altitudes, but at normal altitudes, your red blood cell concentration is normal. And so this means that you're healthy, but it still has an impact. And so it has an impact on your susceptibility to malaria. So yeah, if you have this type of beta globin polypeptide production, then you're sort of in a way resistant to malaria. So people with sickle cell disease are resistant to malaria, but they have sickle cell anemia. If you don't have, if you have both alleles, which is called heterozygous. So if you're heterozygous, then you're you're resistant to malaria, but you're also your blood cell shape is normal. So in a way, this is a sort of advantage in a way can be thought of as an advantage in a way for areas where malaria is endemic. So if we look back at the map, malaria is pretty endemic in these areas. So sickle cell anemia is also sickle cell anemia is also quite prevalent, a little prevalent in these areas. So um, so yeah, we can see. So now this has to do with genetics, right? So we can transition hopefully to a sort of brief thing on genetics. All right, so we talked about every person having at any particular gene having one allele from the mother and one allele from the father. Uh, these alleles might be like M and big M and little m. And so say for example that little m is actually a new mutation, right? So we have big M being the status quo, what's normal, and then little m being the new mutation. So say the father has this and the mother has the normal allele. So let me see if everyone's muted just to be sure. Oh yeah, and thanks Naveen for the correction. Yeah. Let me just mute everyone. Okay. So if you have a father with who's heterozygous, who has both alleles, and a mother who has the normal trait, then what is the probability that you have? What is the probability that you have that this new mutation, say this is a new mutation, what is the probability that this new mutation survives into the next generation? Okay, so this person right here gets one allele from the father and one allele from the mother. So the allele from the mother, because both of the mother's alleles are M and big M and big M, we definitely have a big M from the mother, right? But then from the father, there's a 1/2 chance that this is a big M, and a 1/2 chance that this is a little m. So there's um, a 1/2 chance that the allele does not, the new mutation does not survive. Here, well, same way, the mother passes on a big M, and the father has a 1/2 chance of passing down a big M and 1/2 chance passing down the little m. Okay, so 1/2 chance of big M in this child and 1/2 chance of big M in this child. And so there's a 1/2 chance, or 1/2 times 1/2 chance, or equals 1/4 chance that they'll be both big M's. So big M for this child right here, and big M for this child right here. Okay, so that means there's a, out of the total probability, which is 1, taking away this 1/4 chance that both children are big M and big M, are big M children, there's a 3/4 chance that we have some big M, little m in one of the children. Okay, so now if we look at the next generation after that, so say here we have big M, or big M, little m. Okay, so say here we have big M, little m, and here for the mother we have big M, then the child is has something, and has children with someone with big M, which is someone with the normal alleles and not the mutation. Then what if we look at the probabilities for the next generation? So that will be, so if we look at person 1 here, person 3 here, and person 4 here. So we said that there was a 1/2 chance that person 1 would pass on, would have this little m. And one way people might approach this is, you might think, okay, so well, 1/2 chance here, and then so then for person 3, there's a 1/4 chance that it'll still be passed down. So 1/4 chance that it's still passed on. Okay, my computer's being kind of slow in typing, so 1/4 chance of being at big M, little m. And so there's a 3/4 chance of being big M. And same thing with 4, right? So we might think, okay, so if there's a 3/4 chance that that 3 is big M, and a 3/4 chance that 4 is big M, then there's a 3/4 times 3/4 equals 9/16 chance that both of them are big M. Well, what about 1? So the thing is, we didn't consider the 2 cases for 1. For person 1. If we consider those cases, then we would get right here. So there's a 1/4 chance that 1, or 1/2 chance that 1 is big M, little m, and a 1/2 chance that 1 is big M, big M. Okay, so in the former case here, in the case that it's big M, little m, we have then for person 3, uh, and for children 3 and 4, what are the what is the probability that this little m dies in the next generation? Well, we actually calculated that in while doing the one generation case. So there's a 3/4 chance that the mutation survives. So 3/4 chance that the mutation survives. And for the case that it's big M, then well, uh, person 3, child 3 inherits a big M from the father and inherits inherits what from the mother. Well, we look here, there's only a big M to inherit. So child 3 is big M, child 4 is big M, and so there's a 0 chance that the mutation survives. So ultimately, there's a 1/2 times 3/4 equals 3/8 chance that the mutation survives. So here, what was the crucial point here? Why can't we just multiply 3/4 times 3/4? It turns out that when we multiply 3/4 times 3/4, we're considering these two cases separately as independent. But the thing is that they're not independent, right? So that's something to watch out for in probability, I guess. And okay. And yeah, so the hopeful thing here is that sickle cell anemia with the Black Panther Party's contributions, they were able to really normalize, help to normalize the concept of healthcare for all. So we really have the Black Panther Party to thank for some of our discussions on really like getting healthcare to um, as many people as possible. And so let's see. So another problem, another legacy of enslavement and the marginalization of Black people is maternal mortality. Okay, so where was it? United States. Yeah, Black women in the United States are dying at higher rates than white women in the United States, and has one of the worst mortality rates despite it being a developed nation. So I think it was said that the mortality rates for Black mothers are in the United States is similar to the mortality rates for mothers in, I think, Mexico and Ukraine. So so why is this? There are a lot of reasons for this, but one of them is that Black pain is not taken seriously. So if we look at, say, this article right here, they recruit Black and white. Oh, yeah, I shared another screen. If we look here, there are, so they they took the assessments of pain intensity from Black and white people and other minorities. And so usually they rate the pain on a scale of 0 to 10, and the physicians also rated the pain in order to see how they align. And if they disagree sufficiently, then that also means that the physicians are either overestimating or underestimating the patient's pain. And what it found was that underestimation of pain um, was higher for Black patients than for non-Black patients. So there are a lot of uh, there are a lot of things that we might consider other factors, right? So this takes into account those other factors, but it's important to always see what those confounding factors are and correct for them using, say, software or something like that. And so one of one of the things with so if we look at these statistics, it will say an age and like a mean age and a standard deviation. So this SD means standard deviation. Okay, and what standard deviation is something more than just what we learn about in school usually about mean and median and mode, right? So if we look at probability as a whole, it's not just like you roll a dice. Like if you roll a dice, then you might get a 1, you might get a 2, you might get a 3, 4, 5, or 6, right? And these probabilities are just about equal. Unless you have a weighted die, say it's weighted more towards 3 than it is towards 4. So the 3 might be higher, say like this. So this is a sort of simplified example of a probability distribution. In reality, though, there's more than just the options 1, 2, 3, 4, 5, and 6. Right? It's not just reality is not just a die. And so if we look at the statistics here, there's a mean and a standard deviation. So the mean, so if we, so what are the total options? It's not just 1, 2, 3, 4, 5, 6, but it's a number from, say, 1 to maybe the oldest person, like 120 or 30 something. So 1, say 50 here, and 100 and 150. So the distribution is not the distribution isn't just like a
Brian, you've gone blank again. We got a black screen and no audio. So turns out that it seems that Brian is left because of computer issues. I think he'll be back. He's back. I'm gonna make him host. There you go.
Okay, so yeah, I think that was yeah. Sorry, everyone. I think my computer just froze and restarted Zoom, but actually, since it's 2:04, I'll just wrap it up here. Um, yeah, so hope people were able to take something away from that. There are a lot of inequities that you can help to. There are a lot of inequities in healthcare and oh yeah, sorry, I'm in Pacific Daylight Time (PDT), so I said 2:04, but for those of you in Central Daylight Time, it's 4:04, I guess. But yeah, hope y'all were able to take something away from that. There are a lot of inequities in the healthcare system um, and uh, as a legacy of slavery and um, the continued oppression of Black people in the United States. So hopefully we can use our math skills to help address those inequities. If whether or not you're going into like health or whatever field, like math, even yeah. So that's it. Hope you have a good Juneteenth and see you next time. Yeah, happy Juneteenth. Stop the recording.